This is the 30-second lecture in the FOA series of lectures on fiber optics. In this lecture, we're going to talk about fiber amplifiers and how they're used to regenerate signals in long fiber optic links. A fiber optic data link works by transmitting from the transmitter on one end to the receiver on the other end through the core of an optical fiber. The source and the transmitter couples power into the fiber, which is then diminished by the attenuation of the optical fiber and any losses from connectors and splices in the link before it reaches the receiver. Sometimes the loss in the link is enough that no regeneration is needed, but sometimes the loss is too high, and then we regenerate the signal. If the loss in the optical fiber is too much, we need to regenerate the signal. There are two ways of doing that. One is a classic regenerator that converts the optical signal back to an electrical signal and then back into another optical signal. The other option is a fiber amplifier, which is more commonly used in today's systems. In the early days of fiber optics, regeneration was done by devices called repeaters. A repeater consisted basically of a receiver followed by a transmitter. The incoming optical signal was converted to an electrical signal by the receiver, circuitry cleaned up to remove as much noise as possible, then the signal was retransmitted by another laser. These repeaters added noise to the system, consumed a lot of power, and were quite complicated, which means they were often a source of failure. They also had to be made for the specific bit rate of transmission, and upgrading required replacing the repeaters, a very difficult task, for example, in undersea cables. Since the 1960s, researchers have known how to make fiber lasers. By doping the fiber with active elements added in the manufacturing process, a fiber could be pumped with an external light source until stimulated emission occurs. While the making of fiber amplifiers was theoretically possible, it was not until 1987 that working models were realized. Major contributors to the development included Bell Labs and NTT. This simple diagram here is not the only way they can be made. The pump laser, which causes the stimulated emission, can be done in a forward direction, a backward direction, or even in both directions. The typical fiber amplifier works in the 1550 nanometer band. It consists of a length of fiber doped with erbium, pumped with a laser at 980 nanometers. The pump laser supplies the energy for the amplifier, while the incoming signal stimulates emission as the pulse passes down the fiber. The stimulated emission continues throughout the length of the fiber, so there is a rapid exponential growth of photons in the doped fiber. As the signal travels down the fiber, it gains power. Gains of 40 dB, 10,000 times, are possible, with power outputs as high as plus 20 dBm, or 100 milliwatts. Most fiber amplifiers today are erbium-doped fiber amplifiers operating in the 1550 nanometer range, typically used for long-distance transmission and DWDM. One of the reasons for choosing erbium is it operates most efficiently around 1540 nanometers, right in the middle of this operating range we need, and can be pumped at any of these wavelengths shown here. 980 nanometers is generally chosen because it's away from the wavelengths that are typically used and it is a wavelength that it's relatively easy to build efficient lasers for pumping the amplifier. The wavelength range of erbium-doped fiber amplifiers is compatible with the range used for DWDM, about 1450 to 1650 nanometers. One really big advantage of fiber amplifiers is that a fiber amplifier can amplify all the signals at the different wavelengths in a DWDM system simultaneously. Only one fiber amp is needed for dozens of wavelengths being carried down the fiber simultaneously. So here is our data link with a fiber amplifier. The transmitter couples light into the fiber, and as it travels down the fiber, the signal level is attenuated. The fiber amplifier boosts the signal level back up, so that even with further attenuation in the link, the signal level is adequate for the receiver. If the signal level gets too low a second time, another fiber amplifier can be used to boost the signal level again, and again, and again if necessary, to make sure that the receiver power level is adequate for the link. We're the Fiber Optic Association, the Professional Society of Fiber Optics. We have many other lectures on fiber optics on our YouTube lecture series, and we have on our website almost 1,000 pages of technical information about fiber optics.